Now we consider not the distribution of a random variable, but the distribution of a function of that random variable, whereby whatever value that variable takes is put through a function to produce some other output. And for the discrete case, this is generally quite straightforward. So if I take a variable x, which 30% of the time it takes the value 1, 70% of the time it takes the value 3. If I have another function that says calculate x squared plus 1, so square x and add 1 to it. Well, x is discrete, so x squared plus 1 is discrete, and given that x can only be 1 or 3, then x squared plus 1 can only be 1 squared plus 1 or 3 squared plus 1, so it can only be 2 or 10. So I think it's fairly straightforward to see that the distribution of x very easily gives the distribution of x squared plus 1, that 30% of the time, the 30% of the time associated with x being 1, gives x squared plus 1 being 2, and the 70% of the time associated with x being 3 gives x squared plus 1 being 10. The only complication in the discrete case is if the transformation is not 1-to-1. An example of that here, like if I take y, 30% of the time it's 1, 30% of the time it's minus 1, and 40% of the time it's 3, then here the transformation x squared plus 1 maps y squared plus 1. The transformation maps the y equals 1 and the y equals minus 1 case, both map to y squared plus 1 being equal to 2. So in that case, I'd have to just combine the probability masses where two of the variables outcomes mapped to the same of the function's outputs. But apart from that, that's about as difficult as discrete cases get. As you may have been able to tell by how I ended the previous slide, saying that's how difficult discrete cases get with something relatively easy, that's because the continuous case can be quite a lot harder. Because if I just consider an integration by substitution, a definite integral that I is the integral of f of x with respect to x between a and b, that if I then start using a function y of x, assuming this is differentiable, then the integral of f of x with respect to x between a and b would be equal to the function f of y integrated with respect to y, but I'd need to multiply by this dx by dy, integration by substitution, and I'd need to change the limits, not from a to b, but to y of a to y of b. So in general, the density function of y of x will be given by f of x of y multiplied by x dashed of y, so the derivative of x with respect to y. And again, there are complications where the function is not 1-to-1. There's also cases sometimes where the limits of the integral have flipped around. There are similar analogies where these assumptions are not met. I'm just looking at the general simple case here. Where these ideas get a lot harder is in the multivariate case. So if we think back to doing something like an integration by substitution, it required us to know the rate of change of the old variable with respect to the new variable. And in a multivariate case, I've got rates of change of all of my old variables with respect to all of my new variables, and then I would need this determinant of the Jacobian associated with that transformation. So hopefully you've done some multivariable calculus at this point and done double integrals, triple integrals. If not, that's probably a good place to pause and check that. Because I'm not going to go into the details here. I'm just going to give examples. If you're not sure, please go back to your earlier multivariable calculus notes. So if I start with a nice simple case, x is a uniform variable between 0 and 1, y is a uniform variable between 0 and 1, and to make life easy, I'm going to say they're independent. So they both have density function of 1 between 0 and 1 and 0 everywhere else. So writing down the joint distribution of independent variables is easy. I just multiply them together. So I've got 1 times 1 is 1 in the case where both x and y are between 0 and 1 and 0 everywhere else. That bit's quite straightforward. But let's say I want to work out the distribution not of x and y, but of their product, t, being equal to x times y. Because we started with two variables, x and y, we're going to finish with two variables, s and t. Although t is the only one that's interesting, because s equals x is just basically renaming x. I already know the distribution of x, so I should already know the distribution of s. But I'll do this, and if I write s equals x and t equals xy, if I rearrange that to get my old variables of x and y, x is s and y is t divided by s. And bear in mind, I already know the distributions of x and y. They're uniform 0, 1 variables. But I need the Jacobian associated with this change of variable. I need to know the rate of change of x with respect to s. I need to know the rate of change of y with respect to s, the rate of change of x with respect to t, and y with respect to t. So if I work those out, then ds by ds is 1, dt over s by ds, partially, is minus t over s squared, ds by dt is 0, and d by dt of t over s is 1 over s. So I need to know the absolute value of the determinant of that Jacobian. Determinant is just the product of the top left times the bottom right minus the other diagonal product, which in this case is 1 over s minus 0, so 1 over s. So I put all that together. That may look a bit of a mess, but in this case, I think it's quite simple, or much simpler than it might be. The only difficult part really is the ranges of these things. Well, y had to be between 0 and 1, so in this case, t over s has to be between 0 and 1, so t has to be less than or equal to s, and s has to be between t and 1. So if I actually plug all of this in, there isn't anything to substitute into the probability density function because the density function is 1, or 1 times 1. So density function of 1, there's nothing to substitute in. But there is still the change of variables, the Jacobian, the determinant of the Jacobian. So I get 1 times the absolute value of the determinant of the Jacobian, which is 1 over s. So if I want to know the distribution of t, I have to integrate out over my uncertainty in s. So I'm integrating 1 over s with respect to s over the range that s can take. And s can take values between t and 1. So if I work that out, then I will get, well, log of 1 minus log of t. Log of 1 is 0, so I'll get log, or natural log, of t. So what this does tell me is that the marginal distribution of t is just the negative of the natural log, and that's true for t being between 0 and 1, and not anywhere else. So it might not look obviously like that is a valid density function, because people see a negative and they say densities can't be negative. But between 0 and 1, the natural log is negative. So you'd get a negative negative, so you would get a positive value there.